Hey guys, welcome to our Chapter 6 mini lecture. So, we got through 4, right? Hopefully. In Chapter 4, you learned the beginning of something called optimization, which is where you try to find the best possible result for something. Now, we danced around the calculus. We used a lot of math, but not heavy on the calculus. But the videos help you know that, right? Anyway, yeah, you learned how to maximize utility subject to some limitations. In this chapter, we're going to use pretty much all the same math. We're going to change the order on a couple of things, but we're still going to be looking for a tangency condition. So I need to help you understand what the difference is. So I guess I'll just explain what we do in this chapter. So this chapter is on cost minimization. So it's not utility maximization. It's already different. Check out the cool 3D video in our playlist. I think it'll help a lot to understanding why you look for a tangency condition, even though it's something different. But the general idea is that our firm, we're doing this from a firm's perspective, and our firm is trying to produce a certain number of goods, whatever it is it makes. And it wants to do it in the cheapest way possible. So imagine, for instance, you're running a construction company, and then some group says, hey, we need you to build us 10 houses. And the houses all have to meet these XYZ criteria. Well, you've got a quantity that you are supposed to make, and they're going to give you a certain price for it, no matter how much it costs you to make it. It seems kind of arbitrary to say all that, but work with me, all right? So they're like, hey, we're going to buy 10 houses from you for this much each, and the houses have to be all like this. Your job then is to find the cheapest way to make 10 houses that meet their criteria, because that's how you're going to make the most profit possible. They're paying the same amount for the houses no matter how much quality you put in them. So what is the least expensive way? Now, I don't mean cheap like chintzy materials, although that could be a thing. I mean cheap like the least costly way of producing it. And in this chapter, we're going to focus on specifically the choice between labor and capital. So, capital, that's tools and equipment. That's robots, that's tractors, that's hammers and nails. That's computers that are used at your businesses. That's all kinds of stuff, all right? And labor is our measurement of how much effort the firm is buying from people. Could be measured in hours, could be measured in number of workers. Doesn't really matter. It's just L for labor. So our firm is going to try to minimize costs, but there's a limitation, because obviously the minimum cost would be just don't go in business, no laborers, no capital, cost is zero. We don't want to do that, so we're going to minimize costs with the limitation that we have to meet the order, the quantity prescribed. So in chapter 4, we had to maximize utility subject to a constraint of our budget. In this one, we're minimizing costs subject to a constraint of a minimum quantity. They're both going to look like tangency conditions. Check out the video. It's pretty dope. Anyway, let me just give some spoilers on it, all right? I'll motivate. There's enough videos to give you like the technical content. Let me just give spoilers. The gist of it is going to be that capital and labor both have diminishing returns. If you have the same number of workers and you keep throwing more tools at them, you're going to find that there's a pattern where the first couple of units of capital will have a lot of impact. But as you keep adding more, the additional impact is less and less, because the same workers can only use so much stuff. We call it diminishing marginal product of capital. What's marginal product of capital? That's new products, new production that comes from the next unit of capital. There's that word marginal again. It always means the next unit. Marginal product of capital is new product from the next unit of capital. Likewise, marginal product of labor is new product from the next worker. So, hopefully that helps. Anyway, the firm has to pay money to use capital. In our model, that's just R for rent. That could be actual rent. That could be a bill pay on a loan. Don't overthink it too much. It's just the price of a unit of capital. And there's a W for wage, the price of a unit of labor. And you're going to find yourself that in order to get tangency, the math's very similar. In chapter 4, there was this condition, right, where MUX over PX had to equal MUY over PY to be optimized. Well, in this one, there's a very similar one. MPK over R equals MPL over W. And what is MPK over R? That's new product from the new unit of capital per dollar spent on capital. That's another bang for the buck kind of condition. MPK over R equals MPL over W means that in a tangency point, when you're optimized, a dollar spent on capital gives you the same output as a dollar spent on labor. If a dollar spent on capital brought more return than a dollar spent on labor, you're not optimizing, because you'd be better off spending one less dollar on labor and one more dollar on capital, and you get more product for the same dollar. If the bang for the buck on labor was more than capital, you're not optimizing, because you'd be better off reducing capital and increasing labor. The end result, or at least part of the end result, there's more of course, is going to be that those two things have to be balanced out. So I want to take us through a little bit of imagery. I picked farming just because people don't often realize how high-tech farming gets. Okay, there's a lot of different versions of farming. Here's a picture taken of these guys who are harvesting their crops by hand. They have little knives or scythes and they go through and they harvest it. That would be an example of lots of labor, not a lot of capital. Other versions of production. Here's a couple of guys and a horse and a plow. I guess you'd probably call the horse capital, but yeah, sorry if you're a horse lover. So that's some labor, some capital. Nowadays, instead of something like this, where you have people pulling the plow, you can have something like this. So this picture obviously is one that shows more capital and relative to labor, right? There's a lot more equipment per worker in this picture than in the old ones. And so it gives you some idea of how we can mix lots of labor, a little bit of capital, lots of capital, a little bit of labor, or some sort of mix, which is the one that is most cost effective. It's going to depend on a couple of things: our production function and its shape, as well as the cost of capital and the cost of labor. That's it. Okay, so what's a production function? It is our mathematical model. Okay, it doesn't have to be perfect, but it should have some general traits we like. It's our mathematical model of how capital and labor lead to new output. In most industries, we want to see more capital means more output, more labor means more output, but we want them both to have diminishing returns. Most industries. There are some exceptions, but that means that we usually want some kind of a mix instead of all of one or all of the other. For instance, in this picture of this super crazy industrialized farm, there are still workers driving those things. All right, so let's come back to this little picture, or anything like it. This is a fairly recent picture of a bunch of people farming by hand. And how does that compare to the picture behind me with the big industrial setup? Same modern day. It's not just technology growth. Why are those people all doing by hand what this one doohickey behind me, that thing, can do 10 times faster than all of them put together by itself. Why? Well, it has to do with a couple of things. One is, that picture's probably from a different country where people have much lower wages. And if the price of one of your inputs, capital or labor in this case, is lower, you substitute towards the cheaper thing. Okay? You would not put that many people cutting grass by hand in the United States. But in some places where people often only get paid $1 a day in some like really poor circumstances, that's a very different scenario. Where, you know what, even if this big machine's better than a person, the person is so much cheaper. Another thing is they might not have an order big enough for their company to afford investing in a machine like this one. But that's, yeah, whatever. But yeah, that's how you can have same world, same technology, totally different production functions. Or sorry, totally different production choices. Yeah, in this chapter, you're going to spend a lot of time kind of working through the math and finding out the ideal mix of capital and labor. Real world examples of this at play, or of like, so not someone's like mathing it all the time, but when people say, oh, they're afraid minimum wage is going to kill jobs, well, that's like a real concern. If you raise the wage, MPL over W gets smaller, which means you want to substitute towards capital with a higher MPK over R. So like legitimately, if you make my labor more expensive, I'm inclined to lean at least a little bit of the way to capital. Likewise, as technology grows and becomes cheaper, the price of capital can fall, which also can make us lean towards more capital. Now, I'm going to get on a little bit of a sidetrack here, just something I find fascinating. Take a look at this picture behind me. All right. If you're not familiar with farming, that just looks like a harvester and a tractor thingy. I don't know the exact words for those things. But let me tell you something I learned a couple years ago that fascinated me. Those are actually super high tech. Right? They have GPS tracker stuff in them that says exactly where they are in the field. And there are armies of data scientists behind the scenes here, where they have figured out how to program the computers in these tractors to track everything and to use it. So for instance, as this tractor drives around, it pays attention to how much seed it drops. And then later, when they go and spray their pesticides and herbicides and fungicides on it all, it tracks how much it sprays in different parts of the land. They can track how much water they spray. And then later, when they harvest, that sucker can track how much stuff they're harvesting out of the ground. Exactly where it is. And maybe you're data driven enough that you can kind of see where this is going. But if you can track where you put all your inputs and then your output, computers can make use of that information. In this case, it will actually adjust the settings for next year and spray different amounts of herbicides or fungicides or pesticides in different places. It will water different parts of your land with different amounts. It like optimizes everything to get the most bang for your buck, to get the most output for all of your different inputs. And that's a much more complicated version than our little 2-input model. But you might be able to imagine kind of like a 20-input model with like NMP, K and L and X, Y, Z for all the different inputs. and it can reallocate the resources to get the most bang for the buck all around. Which is why even as fewer and fewer farmers work as farmers, farmers produce more and more stuff than they ever used to. It's pretty fascinating if you get into it. Anyway, one last thought. Let's look into the future a little bit. This isn't really required for the chapter, so if you want to bail, go ahead. But I gotta show you this cool video. So speaking of farming, there's these little drones that are, this is a new thing. This isn't like widespread, but it can fly around, look at your fruit that's growing, and then it's going to detect whether it's ripe or not before it harvests it. They fly around, they balance, they grab the good stuff, they put it in a box where it's supposed to go, and they keep going. And these suckers don't get tired. They can work 24 hours a day. They collect tons of data, kind of like that little farm tractor does, which allows for more involved decision making for data savvy entrepreneurs. But what's going to happen in the future with this stuff? Well, as we know, wages are rising, and we are getting better and better substitutes for our labor. And as those substitutes get cheaper, we're going to see a continual shift in these industries where jobs that used to get done by people don't need to anymore. Now, that's not a doomsday. I'm not saying that there will never be human jobs. That's not how it has worked historically. There have been lots of times in history where people have been like, oh no, this is going to kill all the jobs and no one's going to have anything to do. We always find a way, right? People are pretty industrious. But it does mean that the structure of what kinds of jobs people do is changing. And a lot of it's due to the intuition we derive in our model in chapter 6. Last one, and then I swear I'm done. Self-driving cars are fascinating. You might have already seen news articles about self-driving cars and self-driving trucks. But let me explain why, not like right now, not in the next like 2 years, but why if you look forward a decade or two, the trucking industry or the transportation industry is going to look completely different. Right now, you got these big old trucks that a person has to drive, and they are regulated by how much they can drive every day. I forget if it's 8 or 10 hours, but they're only allowed to drive so far. Why? Because we don't want tired truckers on the road getting us all killed. Not only that, but they're human. They're subject to distractions. They can be checking their Facebook or eating their food or whatever they might be doing. Not that you should do Facebook while you're driving. That's stupid. Texting too. Let people do it. They can get tired. They can get inattentive. Here's the thing. Self-driving vehicles never lose their focus. And the more they drive, the more they collect data, the more they know how to drive. They also don't get tired. And so they won't have to have that like 8-hour limitation. They can drive all through the day. So you have something that can drive safer than a regular person and can drive 2 or 3 times as long per day compared to a regular person. As that technology gets more available and as they get enough data to make it better and better, yeah, it's not going to be good for future truck drivers. But that's a gradual thing. It doesn't have to happen right now. It's just kind of interesting to think about. So I know I got on some crazy sidetracks, but the stuff in this chapter is fascinating. And if you dig into it, you can explain it all using this model. Anyway, I got to get going because this video just keeps dragging on and I keep getting interrupted. I don't even know where I left off. So hope it was useful or at least interesting. And then I hope the technical videos are also interesting because they'll probably help more with the homework. Good luck, guys. Have fun.